Okay, so we start with a simple question. You got water inflowing at 130 Fahrenheit. You've got a container, 2-gallon container full of water at 105, and you want to keep it at 105. And if you do keep it at 105, then the outflow is going to be at 105. Okay? So your heat content per gallon in here changes by how much? Well, I got to tell you how much it changes. It changes by 10 kilojoules per Fahrenheit degree. Okay? So if this went up a Fahrenheit degree, you'd have 10 kilojoules for each gallon, 20 kilojoules for the 2 gallons. Okay? Now, you also have heat loss from the container to the room. Now you've got water, 130 degree water flowing in here. We'll deal with that in a minute. But you got heat loss to the room at a rate of 4 kilojoules per minute. Okay? So at what rate should water flow in to maintain 105 degree Fahrenheit temperature? It's actually a pretty straightforward problem, but you're probably not used to thinking in terms of heat content. It's just another mixture problem. And at this point it's simple, it gets a little harder. Okay, so, well, the heat content has to remain constant, so the heat in has to equal the heat out. Okay? So how much heat comes in here? Okay? Well, you got 130 Fahrenheit water, 105. Well, okay. We're going to translate this to the question. The thing you want to adjust is R. You don't know what the rate is. You don't know what the rate of inflow is. So we're going to let R be the rate of inflow, which is what we're going to actually try to find, and also of outflow. Okay? And then what's the rate of change of the heat content in the container? Well, suppose first that R is, we're not sure how to symbolize this, okay? So what we do is we just assume some arbitrary inflow rate, gallon per minute, which turns out to be pretty excessive, but it allows you to begin getting a handle on what's going on here, okay? At 1 gallon per minute of the water, this water, and I should probably say this incoming water, that 1 gallon per minute that comes in there is going to cool to 105 Fahrenheit. Okay? Its temperature, therefore, changes by -25 Fahrenheit, so it gives up 250 kilojoules as it cools to the 105 degrees. Okay? Now, in reality, if you have that much flow coming in, you're going to have a hard time keeping the temperature here at 105 degrees. But we're assuming that happens. Okay? So if it cools to 105 degrees, it's going to give up 250 kilojoules. Because, of course, it's giving up, it's 1 gallon per minute, losing 10,000 kilojoules for every Fahrenheit degree. 25 degrees, 250 kilojoules. Okay? Now, the loss from the container to the room is only 4 kilojoules in a minute, so this is really overkill. Okay? A gallon per minute is going to pretty rapidly raise the temperature almost to 130 degrees. Okay. So, I just say this is going to rapidly increase the temperature in the container. Okay, so I'm saying here now that 4 250ths of a gallon per minute, which follows immediately if you think about these numbers and what's going on, that would replenish the heat lost from the container. Okay? And that's the answer to the first question. Okay? Now, another question. What if we want to raise the temperature to 110 Fahrenheit in 10 minutes? And for first try on the question, we're going to ignore the increased rate of heat loss to the room. And we're going to let Q equal the heat content in the container. that's going to turn out you need to let Q be the heat content relative to some temperature. And we're going to do probably relative to 105 Fahrenheit. We'll see why we want to do that. Among other things, the heat content will be relative to absolute zero. And water goes through a lot of phases from absolute zero up to 105 Fahrenheit. We don't want to mess with that. We're just dealing with liquid water here between 105 and 130 degrees, right? Okay? Anyhow, so at any instant, the temperature, what's the state of the system? State of the system is specified by the temperature. And then we have the inflow rate. And we're going to kind of implicitly let Q stand for the quantity of heat. I think I said that. Yeah, I just said that. Okay, at any instant, the temperature of the container's T, rate of inflow is R. At what rate is heat flowing in, and at what rate is heat flowing out? Again, you may be, if you're fairly experienced in doing these things, be able to just write this down symbolically. There's a better chance at this stage in the course that most students are going to need to get a handle on just what the heck is going on with that. So we get a handle on the idea by just picking some numbers. Okay? Temperature is going to be between 105 and 110, so let's just pick 107 degrees. Then, since 4/250ths of a gallon per minute maintains the temperature, we know that if the temperature is going to be increasing, we better have more than 4/250ths of a gallon per minute flowing in. But we're not increasing the temperature that much or that quickly, so we don't want to pick like 40 gallons per minute or something. Okay, we saw that even a gallon per minute is excessive. So we want to do something comparable to this, but a little bigger. Well, 4/250ths is 0.016. I'm saying 0.02 is convenient. Okay? It's the nicest, roundest number near 0.016 that kind of makes sense in this situation. Okay? We're not trying to solve the problem here. We're just trying to get a handle on it. So we can pick any two numbers, any temperature and any number here. We want to see how the temperature and the inflow rate work together. Okay? Okay, well, then, if the temperature stayed at 107 for a minute, now, next question, we're still not sure what to do with this, but we just say, okay, the temperature's 107, at what rate is heat flowing in? If we just assume the temperature stays at 107 for a minute, then we ask the question, how much heat would the inflowing water lose? Now we know the temperature's not going to stay at 107 Fahrenheit. If we have a rate better than the rate that replenishes what's lost to the surroundings, the temperature's going to keep increasing, but let's just pretend it stays here and ask how much heat is the inflowing water going to lose? Well, pretty easy to answer that. In 1 minute, 0.02 gallons is going to cool from 130 to 107. That's what's going to happen. Okay, you want to talk about, okay, here's what's going to happen in a minute. And then you translate that into the things you want to know. 0.02 gallons is going to lose how much heat to the water? Well, that's easy. 0.02 gallons and I didn't do all the stuff with the units here that you do, but it should be intuitively clear that if 1 gallon loses 10 kilojoules for a degree, 0.02 gallons loses 0.02 times 10 kilojoules per degree. So this much, 0.2 kilojoules in a minute for every Fahrenheit. Okay? And the water cools by 23 Fahrenheit, so you multiply this by 23, and you find it loses 4.6 kilojoules. So when the temperature is 107, the rate is this, you get a rate of change of the heat content of 4.6 kilojoules per minute. Rate of change of the heat content of the incoming water. And I should say that's negative 4.6 kilojoules per minute, because the incoming water is losing, but the mixture in the container is gaining that. So that your rate of change now, your dq dt, so we're starting to approach a differential equation here, is 4.6 kilojoules per minute, minus the 4 kilojoules per minute that you're losing to the surroundings. Again, to be clear, incoming water loses this. Where does it go? It goes into the water in the container, which of course includes the incoming water, but you should get that idea, okay? Which means that you're increasing at 0.6, net rate of increase would be 0.4, would be 0.6 kilojoules per minute, okay? Meaning it takes 16 minutes to increase the temperature a degree, because you need 10 kilojoules to increase by a degree, okay? So this incidentally tells you, I did write it down, I didn't talk about it when we were drugging it out of you, or trying to instill it in you, but clearly from this result, if you just think about what this means, 0.6 kilojoule per minute net change, taking 16 minutes to increase by a degree, in order to accomplish our goal of going from 105 to 110 in 10 minutes, it's going to have to be somewhat more than 0.02 kilojoules per minute. Okay? So, we have this. Now, to get from 105 to 110, we need to increase Q by 100 kilojoules. So, at this stage, now when Q is increased by an amount delta Q, what is the temperature and what's dq dt? Now the example here that I try to use to clarify the meaning of this is, well, just say Q is increased somewhere between 0 and 100 kilojoules. Just pick 60 kilojoules. Okay? Temperature would be 108. You have a 22 Fahrenheit loss and so forth. The same thing we did here tells you you have a 4.4 kilojoule per minute contribution from the water that's coming in. You still have a ways to go to come up with a differential equation. Once you do it, I think it's very hard to solve. But coming up with the equation is the big deal. Now all this could have been done in standard physics terminology, but either way, they had the physics, so I didn't want to confuse the thing. I wanted to keep it as intuitive as possible. Okay? Now, when I pose the problems for homework, the one problem, this is going to be it. I'll give you a few more, just a little more guidance. Okay? Then I'll give you the real problem when the thing is losing heat to the surroundings, and then you can meditate on whether you can solve that equation or whether you need to go to numerical methods. Okay? Good.